Good morning here. In this lecture, in the last lecture, actually we learned about the atomic mass number, atomic number, and isotopes. Okay, now again I'm going to repeat here. What is atomic number? Atomic number is represented by the Z, capital Z. Mass number is represented by the A, capital A, and this is the representation of a nuclide. So nuclide means the composition of a nucleus. Here the superscript is left hand side is represented with the mass number A, and the subscript on the left is represented with the Z, that is the atomic number. Okay, also I have given you the numerical or the problem simple, that is argon having the mass number 40 and the atomic number 18, and you have to calculate the number of protons, electrons, and neutron. So here the number of protons will be equal to Z, that is 18. Number of electrons becomes the same as that of proton, so it becomes here again 18. And now the number of neutrons, it becomes atomic mass number, that is A minus the Z, that is the proton, so it becomes 40 minus 18, it becomes 20. So these are the number of neutrons. Okay, now we'll go for the next, that is called as isotopes. What is mean by isotopes? Isobars and isotones. So let's first study about the isotopes. Okay, I'm going to represent here the PPT. Now here, I think in the last lecture, we are up to this numericals, okay, of argon and carbon. Okay, then we go for the next, that is called as isotopes and isobars and isotones. Okay, so what are isotopes? So these isotopes are the atoms of the same element. See here, the main very important thing, that isotopes are the atoms of the same element having the same number of protons, because these are the atoms of the same element. So number of protons becomes the same, and they are differ by the number of neutrons. So for example, if you take carbon, so carbon is having carbon 12, carbon 30, and carbon 14. Carbon 12, carbon 13, and carbon 14. Okay, now this carbon has three isotopes like this, 12, 13, and 14. So it is 12. 12 here is a mass number. So one of the isotopes of carbon is carbon 12, another isotope of carbon is carbon 13, another isotopes of carbon is carbon 14, having the same atomic number, that is 6, and they are differ by the number of neutrons. Okay, so here in this chart I am just showing here. So uh, just look at this table here. In the first, it is given the symbol. So this is a symbol to represent the each isotopes, carbon 12, carbon 13, and carbon 14. So you have to read like this, the isotopes carbon 12, carbon 13, carbon 14. The atomic number for carbon 12 isotopes is 6. Okay, atomic mass number is 12. Hence the number of neutrons become 12 minus 6, that is 6. Okay, now what is abundance? It is given as 98.9% abundance, that is natural abundance, and stability here it is stable. So what is mean by abundance or natural abundance? Now these isotopes, now each compounds, there are compounds, elements, and molecule. You know the difference between elements, compounds, and what is mean by the atoms. Okay, so compounds are, it is the aggregation of two or more elements or combination of two or more elements to form a different substance, that is called as a compound. So in a compound, if carbon is present, then carbon is exist in all these three isotopes, is exist in all these three isotopes. So it contains 98.9% that of carbon 12 atoms, means all the atoms of carbon, in which 98.9% atoms are of carbon, and 1.1% carbon atoms are of that carbon 13 isotopes. Okay, and less than 1% means to a, I think in the range of 10 raised to minus 10 will be the percentage of carbon 14 atom. So in a compound, carbon exists in all these three isotopic forms, or these three different atoms of the same element, that is carbon. What is the percentage of carbon 12? Carbon 12 percentage here is 98.9%. What is the percentage of carbon 13 is 1.1, and carbon 14 is very very less percentage. That is called as a natural abundance. So in earth, carbon exists in these three isotopic form. So out of this, carbon 12 is the stable one, okay, which is shown in this table. Then carbon 13, if you take the second isotope, that is carbon 13, atomic number is 6, atomic mass number is 13, number of neutrons are 7. So 13 minus 6 becomes 1.1, sorry, 13 minus 6 becomes 7, so number of neutrons will be 7. Okay, natural abundance is 1.1%, and this isotope is a stable one. The third isotopes of carbon is carbon 14. It contains, the atomic number is again same 6. The mass number is 14. Number of neutrons becomes 14 minus 6, that is 8. Okay. And the percentage natural abundance is very, very less. And it is a radioactive one. So this, you know that carbon 14 is, you know, it is used, it is a radioactive isotope. Carbon 14 is a radioactive isotopes, and it is used to calculate the age of the things. Okay, different things. Okay, now this is all about the information of the isotopes. There are another examples of isotopes are also there. For example, you can say here the hydrogen. So hydrogen will remain in the form, three isotopic form, that is hydrogen, second one is deuterium, and third one is a tritium. So all these are having the number of neutrons are different. So for example, if you take hydrogen, then hydrogen contains only one proton, okay, and one electron. Deuterium contains one proton, one electron, and one neutron. So mass number becomes 2. Okay, and for the tritium, for the tritium, it contains one proton and two proton and one neutron, so mass becomes 3. Okay, so this way, one proton, sorry, and two neutrons, so mass becomes 3, mass number becomes 3. So this way the different elements exist in this different isotopic forms, but it is not, compulsory, or it is not, it is not the rule that all the elements should have isotopes. There are some elements which does not exist in the different isotopic forms. For example, fluorine. Okay, now this is all about the isotopes. Okay, then we go for the next, that is called as isobars. Now what are isobars? So isobars are the atoms of the same element having the same mass number but different atomic numbers. Again, here there is something is wrong. These are the atoms of the isobars are the atoms of the different elements. It's not the same here. Atoms, these are the different elements. It's not the same here. And having the mass number is same, but it contains different atomic number. So because these are the atoms of the different elements, so that's why their atomic number is different. But their mass number is same. Somewhat it is same. So even if it is same, these are the atoms of the different elements. So if you take the here example as carbon 14 and nitrogen 14. Okay, so the mass number of carbon is 14 here. Okay, this is the representation of the nuclide in this first column. Isobars, these are carbon and nitrogen. These are the examples of the isobars. So if you take carbon, this mass number is 14 and atomic number is 6. Okay, and here we can say that atomic number is 6 here, mass number is 14. So number of protons is 6 because mass atomic number is 6. number of neutrons becomes 14 minus 6, that is 8. For nitrogen, the mass number is 14, atomic number is 7, number of protons is 7, and the number of neutrons becomes 14 minus 7, that is 6, that is 7. So in the definition, the important thing is that these are isobars are the atoms of the different element. This please correct it. Okay. And these are the atoms of the different elements. So what is similarity? Similarity is only that they are having the same mass number. They are having the same mass number, and we know that they are, if they are the atoms of the different elements, then of course the atomic number is different, number of protons is different. Okay, so mass number is same, atomic number is different, called as a isobar. Example is carbon 14 and nitrogen 14, carbon 14 and nitrogen 14. Okay, now we'll go for the another thing, another topic, that is called as isotones. So what are isotones? So the isotones are the atoms of the different elements. Isotones are the atoms of the different elements and having the same number of neutrons. They are having the same number of neutrons, and of course their atomic number is different because these are the atoms of the different element. So the atomic number is different, but they have the same number of neutrons. They are having the same number of neutrons. That's why they are called as isotones. Okay. Example here is carbon 12. So here carbon 12, carbon 12 means mass number 12 here. So this carbon 12 and boron is are having the isotones, means they are the example of isotones. So boron 11 and carbon 12, these are the isotones. Okay, so in the first column the isotones are boron 11, carbon 12. Calculate their atomic number. So for the boron, the atomic number Z is 5, mass number is 11, number of neutrons becomes 6. 11 minus 5, it is become 6. Okay, for carbon, if you calculate, the atomic number is 6. Okay, from the representation we can easily predict that its atomic number is 6. Okay, and mass number is 12 from the representation. Okay, it is 12 mass number. So number of neutrons is a minus z, so that is 6. I think you understand this. Again I'm going to explain this for the carbon. So for the carbon 12, what is a? Mass number is 12. What is the value of z? That is atomic number is 6. Okay, so right here atomic number 6, mass number 12. 12 minus 6, number of neutrons are 6. And if you look at in both these cases examples, the number of neutron is 6, and 6 means isotones are the atoms of the different element having the same number of neutrons, and they are called as isotones. Now if you look at the example again here, the mass number is also different and atomic number is also obviously different. Mass number is also different, atomic number is different, but what is similarity in the isotones? They are having the same number of neutron. So this way I think this is very important, the isobars, isotones, and uh, isotopes. Okay, and we learned all these three things. Okay, now the examples of this I think I have given the examples. I have taken all the examples. Okay, and I will also give you some examples in the end of this video. Okay, now we'll go for the next, that is called as a problem 4.3. It is in your textbook. I'm going to explain this. Okay, so that you can understand how to solve the problem. So there are three elements Q, R, and T, and they are having the mass number 40. Their mass number is same, that is 40, and their atoms contains 22, 21, 20 neutrons respectively. So you have to represent their atomic composition with appropriate symbol. Represent their atomic composition with appropriate symbol. So solution here is, you know, we know the formula A is equal to Z plus N. Okay, A is equal to Z plus N, or Z is equal to A minus N. Z is equal to A minus N, or N is equal to A minus Z. Okay, that is all is correct. Okay, so for the given there three elements, okay, A is equal to 40. We know that mass number is 40. Now we are going to calculate first, that is Z, because neutrons, that is N is given, A is given. So I have to calculate the Z of each element Q, R, and T. Okay, so in the above expression, for Q is equal to Z, for the Q, so Z means the atomic number Z is equal to A minus N, is equal to A minus N, and 40 minus 22, because N is 22 for Q. So 40 minus 22 becomes 18. For R, for the another element, that is R, Z is equal to A minus N. Z is equal to A minus N again. So 40 minus 21. 21 is the number of neutrons. For R, the number of neutron is 21. So 40 minus 21 becomes 19. Okay. And for the Z, for the T element, Z is equal to again A minus N, that is 40 minus 20. 40 minus 20 is equal to 20. So this way it's very easy to calculate the protons, number of protons, number of electrons, and the number of neutrons. So always say that it's easy, the things become easy. Okay, so the atomic composition, how can you write now? How to write the composition? Because you have to write this in the composition, means in the formation, in the representation of a nuclide. Composition means, atomic composition means you have to represent the nuclide in this form. So the Q element can be represented with, how can you represent the Q element, is like 40 on the left hand side at the superscript, and 18, okay, which we have calculated 18 N, so it becomes subscript to the left hand side. So this way you can calculate. So Q becomes here 40 and 18. Okay, R, it becomes 40 is remaining the same, 40 and 19. Okay, and T becomes 40 and I think it is 20. Okay, so this is the representation for the Q, R, and T elements. Okay, so this is all about the problems 4.3, and then we go for the little bit um, information about the Rutherford's experiment. Before that, I'm going to explain that what we are learning. We are learning the atomic structure. We are learning the atomic structure, means we know the subatomic particles, protons and electrons. Okay, neutron is discovered later in 1932, but at that time they know the protons and the electrons, but they don't know where are these protons and electrons. So the arrangement of protons and electrons in an atom is called as a model of atom. Arrangement of the subatomic particles, proton and electron, in an atom is called as a model of an atom, or the structure of an atom. And the many efforts are taken place at that time to put forth the model of an atom. The first time, the first model of an atom is put forth by the scientist Thomson. Second effort is made by the Rutherfords. Okay, and third is by Bohr's. So Bohr's model of an atom, and the next is called as a quantum mechanical model of an atom, which is now accepted. Okay, so we are supposed to learn the Rutherfords, then Bohr's in details. Okay, and then quantum mechanical model in details. For the Rutherford's model of an atom, only drawbacks are included in your syllabus. But so as to understand the drawbacks, we must, at least in short, we should know what is Rutherford's model. So I'm going to give you the explanation in very short, that what is Rutherford's experiment and how he put forth his model of an atom. Okay, and then we go for the drawbacks. So this is a experiment setup for the Rutherford's experiment that is called as very famous alpha particle scattering experiment. So he has done this experiment where he put the radioactive element radium in a lead block. Okay, the disintegrations come from this and they are strike on the zinc screen. Okay, and he is able to detect this integration. From this experiment he is able to calculate the the disintegrations. Okay, quantitatively means how many integrations are supposed to be there in 1 second. Okay, and which are going through the foil straight, which are deviated to an angle 90 less than, which are deviated to an angle straight 180, which are returning back. From this observation he conclude. Okay, from the conclusion he put forth the model of an atom. I'm going to explain this in very short, 1 or 2 points of his model, and then we go for the drawback. So Rutherford say that the first point or the first postulate or of the Rutherford's model of an atom, that he said that there is a, at the center, all the mass of the atom is situated at the center. All the mass of an atom is situated at the center, and again the positive charge is also situated at the center. As a whole, atom is empty and all its mass is centered at one point in the center. So that he called that as a nucleus. So this idea is very revolutionary, that nucleus is situated at the center of the atom and which contains a positive charge. Okay, second thing is that he said that electrons revolve around the nucleus. Electrons revolve around the nucleus in a circular path. In a circular path. So these two idea are very I think magical idea, that nucleus is at the center of the atom and electrons are revolving around the nucleus. And I think it is true now also. So these ideas are very revolutionary. So this is the there are many points, so I'm just taking in very short. This is the model of the Rutherford's model of an atom. These are the two very important points. Okay, and now we go for what are the drawbacks. So what is mean by drawbacks? Drawbacks means these are the points which cannot be explained by this model. These are the points which cannot be explained. This model is failed to explain certain points. These are called as the drawbacks. So what are the drawbacks of Rutherford's atomic model? The first drawback of Rutherford atomic model is that if the electron, which is a charged particle, electron is negatively charged, he said that, and the proton, the nucleus is at the center. These are the two things. Nucleus is at the center, which is positively charged. So if electron is revolving around the nucleus in a circular path, okay, then it emits its energy, that is called as a radiation. Radiation is same as that of the energy. Okay, so for time being we say that it is a energy. So if electron is revolving around, suppose this is the nucleus and if this is the electron, okay, and if it revolves around the nucleus in a circular path, then it should emit its energy, because it is revolving around a charged particle. So when charged particle is revolving around a charged particle, then according to the other theories it should emit its energy. If it is emitting, losing the energy, then it should come to the closer and closer to the nucleus. If it is coming closer and closer to the nucleus, it should take a spiral path and it is ultimately collapse into the nucleus. This is the important thing, or this is the important drawback, that if a charged particle is revolving around a charged particle, it must emits its energy, it loses its energy. If it loses its energy, it comes closer to the nucleus. Okay, and ultimately the energy, all the energy is emitted, it falls into the nucleus. But this does not happen. Atoms are stable. So this is gives a instability to the atom, and this happening cannot be explained by Rutherford. Means why this he cannot account for the stability of the atom. He cannot account for the stability of the atom. Its model of an atom becomes unstable. Okay, the atom becomes unstable. The second drawback, and we'll finish here. The second very serious drawback of the Rutherford model said that he said that the electrons revolve around the nucleus. He said that electrons revolves around the nucleus. It's okay, it is for the hydrogen one electron, but what about the lead and other higher elements having the large number of electron? For example, lead atomic number 80 means 80 electrons. How the 80 electrons revolve around the nucleus, and what about their energy, what is their position? So this could not be explained by Rutherford. So this is the second drawback of the Rutherford model, that it does not describe the distribution of electrons around the nucleus and their energies. So these are the two important drawbacks. And another also important, that he could not explain the atomic spectra, but which we are going to explain in the Bohr's atomic model. So we will go for the next lecture. In the next lecture, we will go for the Bohr's atomic model. Okay. So we'll be go in the next, that is called as a Bohr's atomic model, in the next lecture.